Hey everyone, this is a quick video to talk about the FRQ from the sequences and series quests, just because it was difficult for many. This can be pretty involved. Hopefully this will untangle it a little bit. So to determine the convergence of this series 1 over e to the n using the integral test, you must first establish that this thing is decreasing, positive, and continuous. It's useful to note that when we have things in terms of n, that's sort of sequence notation. So really think about it as a function with x. So I think you'll get the points on the exam if you were to use n, but it's really better mathematically to think of it as a function like f of x. We don't use n as like a variable in functions. So you can write it 1 over e to the x, or even better, probably e to the minus x. And it must be decreasing. Originally, when I wrote this out, I said and be as clear as possible. Don't just say, the series. Rewrite what it is quickly so that it's really clear what the series is. If you say it, who knows what it is, but if you write 1 over e to the x must be decreasing, positive, and continuous, it's really clear. Okay, so then the integral test, you really need to know how to set up that integral. It's useful because it's also used in our improper integrals, things going out to infinity, or things going areas trapped up along asymptotes. Is an important thing to know, that we don't just write from 0 to infinity. That is wrong. You will lose points. You write it from 0 to b or 0 to k, and then you say what's the limit as that point that you're integrating goes out to infinity. That's mathematically the better way to think about it. Oh yes, going back to our criteria here, I did want to mention that please don't make the mistake that I did that one time in class where you ignore that there's a discontinuity. You need to show that beyond, a point that you are considering for this convergence, that it is in fact continuous. And we know there's a list of functions that are known to be continuous. This is one of them. And of course, polynomials and sine functions and cosine functions are, whereas tangent, cotangent functions are not known to be continuous. So then once you set this up, just know your integration. Some of you guys wanted to go with ln's and things like that. I can understand. But once you write it as e to the negative x, think about what's the derivative of e to the negative x. Well, that's just negative e to the negative x. And integration and derivation with e to the x is pretty straightforward. So it'll perhaps trigger that memory that you just put that negative out in front. And then we have our limits, our bounds of integration there. And when you plug it in, you'll see that 1 over e to the b, as b gets large, it goes to 0. And then this is just minus a minus 1. So we actually get something that then is finite and positive, and therefore we can conclude that this does converge, okay? So as long as we can show that, we have proven that it converges by the integral test. Now, the limit comparison test then is where we've just shown that 1 over e to the n converges. So now we can use that to show that this sequence will converge. And because we're told to prove that it converges absolutely, we can drop off the negative sign. You need to note that it's positive when we're considering, positive only when we're considering the absolute convergence, okay? So it's not about alternating convergence, it's about absolute convergence. So then when we do the limit comparison test, this is different than the landing airplanes. That's the direct comparison test, okay? And that's the analogy that, okay, if we know what this is doing, either diverging or converging, if we know it's diverging and we can show something above it, then that is going to diverge as well. If we know that this is converging and something else is below it, then this will converge as well. The thing below it will converge as well. But if you go back to Kahn, he does a good job of sort of showing the difference between the two, that there are times when we have a function that's easily expressed that's above one that converges, and that doesn't help us. If this thing up here is above the one that converges, that's inconclusive. But that's when the limit comparison test can be useful, because it ties these two together. It links them together And then we can say, well, they're both going to do the same thing. And if we know what this is going to do, then it's going to work. So in that case, we set up a ratio. It does not matter. You can swap these around. I think in the answer key, they actually do swap them around. You're either going to wind up with an answer of 1/2 or with 2/1. Either case, you just want to show that this thing we know, when we set up a ratio and then consider what's that ratio as n goes out to infinity, and it's positive and finite, that the two are linked, and we can say that it converges by the limit comparison test. They really want you to not, like I said before, use the term like then it converges. Be clear about what converges. That's the shortest way to do it. You can also rewrite the actual sequence that's converging. All right, so then on to part C, the radius of convergence. The radius is just like in a circle. When we say, hey, the radius is how far our circle is defined by. So we just need to do the same sort of thing we do with the interval of convergence, but we just care about what is the actual distance away from our x, or what is the center of the limit on either side. So when you go through the ratio test, you set it up, don't forget to write the limit. It's very easy to do that, but we're really talking about the limit as n goes to infinity of the n+1 over the n. And of course, we flip the fraction, we write it. I think this is the mistake that many folks made, that they somehow thought it was 2e to the n+1, but it is not. That's a PEMDAS thing, that we always do the exponent first. So by separating it out, you'll see that they cancel. Many of you got 2e as your interval of convergence, but it is in fact just e, so you can look that over. But it's really this boundary that is going to be then on either side of it. That's just the radius. So very, very similar concept, just a different way of denoting it. The nice thing is that with the radius, we don't really care about whether it's equal to or not. It's just like when you draw a circle, you go out that far and you draw it. You're not really on the circle or not. It's not a concept that is like used. It's only that we need to check these inequality signs by subbing in when we're actually writing the interval of convergence. And there's likely to be something about interval of convergence on the AP exam, so you do want to know that. You put in e and negative e, and you'll see that if it works. Okay, so that's for interval of convergence. And then the last one is just about the error bound for an alternating series, and the I didn't write down the alternating series error is approximated, the series here, as they say, is approximated by the first two terms. So the alternating series error is found by using the next term. In this case, if it's two terms, it's the third term. The tricky thing is just remember it starts with 0. That is that 0 right there. Okay, so we know that the first term is the 0, the second term is the 1, the third term is a 2. That's a setup. It's kind of annoying that they did it that way, but these things often start at 0, so you just need to be ready for that. So when you plug in 2, that's the final answer. It is the absolute value. We're really in error. We're almost always asking about what is the absolute value of the error, what's the most the error can be. Khan does the whole thing about overestimate and underestimate, and I think that can easily make you think that you need to keep track of the sign, but for error, no, you don't. You just use the absolute value. Okay, leave it in exact terms. Hopefully that helps. Thanks a lot.